Hello and welcome to the SaturdayMP show, episode number 46, being recorded mostly live, June 3rd, 2024. This is a show about shipping secure, high-quality software faster, and we do that mostly through live demos and kind of hands-on problem solving. Probably some theory. This one is going to be a little different. There'll be a little bit of theory in this one. But yeah, that's kind of what we do. I'm your host, Chris. And today, like I said, we're going to do a little bit of theory. We're going to talk about the RSA encryption algorithm. And the reason I wanted to talk about that is because a little while ago, I kind of was working through some more of these PicoCTF ones. So I haven't made that far, but I just did this mind your P's and Q's. And it wants you to basically decrypt the RSA algorithm. Basically, the RSA, the keys kind of chosen, the numbers chosen aren't big enough. So, excuse me. So the idea is to kind of reverse engineer what the encrypted value is. So this is the mind your P's and Q's here. And then if we go and download it here, so what am I thinking here? So sorry, this is the message here, and then N, this is like the public key, and E is part of, so these two parts are part of the public key, and this is the message. Given that this is a weak public key, we're going to be able to decrypt it, and decrypt it, we're going to figure out what the private key actually is. But I guess before we get any further, if you just want to solve this a simple way, you can just go to this website here, this decode.fr. And they already have an RSA decoder. So if you put all the values in there, so if you're just looking for a quick and easy solution, no E, we want end here, and E goes here, and then calculate decrypt. Oh, it's thinking. Did I put everything in the right spot? Looks like it. All right, so there's basically, here's all the keys and everything you need, and just to basically give you the answer that you need. So, where does it show the actual? I can't remember if it shows the actual text out or whatever, but anyway, you can get the answer through this website using this decode. So that's a super simple way, right? And so, but kind of, I didn't really understand how RSA works. So over the last couple of weeks, I've been trying to dig a little deeper into it, and I've been reading. I guess you can't see it here, but maybe you can hear it if I don't knock over my water. This big book here, this Applied Cryptography by Bruce. I think it's Schneiner. So I've been reading through that, trying to figure out how RSA worked, and then also some website stuff as well. And so that's been useful for me. So I'll just share what little I know about the RSA algorithm, and maybe others will find it useful as well. Oh, here we can even display as, okay, this display plain text character string. This will give you the answer. So if anyone's looking for the actual answer, yeah, there you go. There's the answer. And this is what we're going to do. We're basically going to do this algorithm, but we're going to do it manually just to kind of highlight how the RSA algorithm works. So basically we should end up with these values here. All right, and I did a little bit of a README there already, like I wrote my thoughts down, but let's add a new file here. I don't know, let's just call it video. Okay, so what we'll do here is, I think my plan for today is we're going to go through the RSA algorithm kind of using a simple example. Basically, I'm going to use the one from Bruce Schneider's books here. Hopefully I'm saying that name right. I should have looked that up before I started the video. But I'm going to go through his example in the book. And then we can, once we do that real quick, then we can kind of reverse engineer the bigger actual one. Because the values here, like these are still pretty big numbers. But when we're going through the example, we're going to use obviously much smaller numbers. So if you have the book, you can follow along. But so some of the interesting things about the RSA, the way it works, is the first thing you do, so I guess I should point out too, I'm not an expert cryptographer or math genius or anything. I actually had to look up some math when I was looking this up. It was funny, my wife saw me like actually doing old like I call it old math, but like my high school university math, and she was like, "What's going on?" So, but I think the idea is for this algorithm to work is that it's pretty easy to if you know the keys, it's easy to decipher. But if you don't know the keys and trying to figure out the actual key, basically you want a thing that figure out like the private key is really difficult. And I'm not 100% sure the math about why this algorithm is actually hard, but anyway, let's just go through it. Maybe it'll come to me again. All right, so the first thing you need to do is you need to figure out this n value, which they always call, which is n equals p times q, or p and q are two prime numbers. Ideally, prime numbers about the same length. So that's kind of like step one is this. And then step two is you need to figure out an encryption key, E. And most of the time, as far as I can tell, there's lots of different ways to figure it out. But from what I'm reading and stuff like that, is it's going to usually be this number here. But it can be a different number. And having a really small E value can be bad. But apparently, I don't know if this number is still valid because the book is actually a little old. So, you know, for those of you who created RSA keys, you know that the values have jumped from, they're up to like 4K or something now, the key length. So it's getting quite big because I think the other keys were easy enough to figure out. So, but the E is, it's kind of this weird algorithm where E times D equals 1 mod, and then you got P minus 1, and then Q minus 1. And this D here is actually going to be the private key. And this is mod the modulus operator. Right, so that you gotta figure out an E that works something like that. So let me see here. Yeah, so you want E, sorry, this is, I'm getting ahead of myself. This is for step 3. This is for figuring out D. But E, it's got some logic that it needs to be like relatively prime to P minus 1 and Q minus 1. And yeah, actually, let's see. So if I go, what the heck does relatively prime mean? Relatively prime. All right, so. Oh, okay, but so the divisor of both of them is 1. Oh, okay, so they don't have any other common divisors. Okay, so we need to pick an E. Again, usually this is usually what's picked, but there could be other ones. But it's got to be relatively prime to this P minus 1 and Q minus 1. And to determine D, you need to do this formula here where E times D equals this, which this is kind of the worst. This is one I had to like, I didn't understand how this, to figure out D worked. This algorithm was a little complicated. So, and then you can encrypt the message. So C is your encrypted message, which is M to the, where's my power thing? To the power of E mod N. And then when you decrypt the message, it's going to be M. So M is your message again. So C is your encrypted message to the power of D mod N. So basically that's the formulas we have to, this is the formula used to create it. And now that we have, so we have these values, we basically have N and we have E and we have C. So the one thing we want to figure out is what is D. And to figure out D, we really need to figure out P and Q. That's kind of an easier way to do it, is to figure out what P and Q are. And to figure out what P and Q are, you can actually get those values. So one of the problems is this N is not a very big number. So there's actually, we're going to, well, actually maybe we won't jump into that yet. We'll show how to do that in a second. Okay, so let's go through the example in the book here. And again, if you have any feedback or corrections or something, please leave comments down below or shoot me an email to ask@SaturdayMP.com. All right, so let's say we pick, so the example in the book is they have P equals 47, and Q equals 71. And that doesn't give you value of N equals 47 times 71, which equals 3337, right? So that's our value of N for this particular example. And then what's the next thing I'm thinking? All right, so then we have to choose E. So I guess this is step 1. Is here, and then we have to pick an E. So remember, E has to be relatively prime to P minus 1 and Q minus 1, and that equals 3. So P minus 1, what's P? 40? So it's 46 times Q, which is 70, which equals, I guess I can bring up, let's see, is there a calculator? There's got to be a calculator here. Okay, so there, we have this calculator if we need it here. Actually, don't have to switch between them. Why don't we just bring up Python here? Okay, so there, we use Python for any math if we need to. So now we have to pick an E that's relatively prime to both of these. And we kind of choose at random. In the book, they choose E to equal 79. So I'm sure there's some math behind it that helps you pick that value of E that I fully don't understand, but it just has to be relatively prime. So and then this is a more complicated one to figure out was what am I thinking here? Is figuring out D. So the formula looks like D to the power of -1 mod 3220. I don't really understand this formula 100%, so I have to go take a peek at my README. But then you have to use this, and again, I'm probably going to get this name wrong, the Euclidean algorithm, the extended Euclidean algorithm. And so this is what I tried to, I was taking notes in this README. So yeah, you're figuring out the GDC of 79 and 32. Yeah, there's 1. So you're all good there. So to calculate this, you have to actually figure out the greatest common divisor of these two numbers. And then you kind of work your way down and then work your way back up again, because you want this formula. You actually want a formula. Where is that? It's basically a formula where D. Wait, sorry, give me 1 second here. Well, I have to go look up the formula again. This is more explaining it to myself, I guess, than anyone else. All right, so. Right, because you're going to want a formula that's similar to. Oh, now I have to look here. Okay, so. Right, so we had. This is the formula. So. All right, so the actual formula was D times E equals 1 mod. It's not quite N, because if you remember, N is this value. This value is actually this P minus 1 N minus 1, which they have this weird symbol for, which I can't really represent on the keyboard really easy. So we'll just call it let's just call it the function of N like that. But that's basically this. So maybe function t, I don't know what to call it. Maybe we'll just call it t. So this is t, basically this guy right here. Let's just call it t. And then, so if you fill in the numbers for that, you end up with this formula. And then if you rearrange the formula, you end up with this. But this is, you can also rearrange the formula so that it looks like this one here. Right, so you have 79 times x plus 220 times y equals 1. Apparently these are all equivalent formulas. Through some math I don't 100% understand. And then what we really want to figure out is this this kind of x value, this d value here. We really don't care about this one. This is what we really want, if I remember correctly. Right? So let's see if we can figure that out. So you can, there's a bunch of algorithms on there. So if you want, you can look up the I'll type it out in case people want to look for it. But you can find Python and stuff like that. So it's the extended algorithm. And then if you actually look at here, I think it'll tell you yeah, so did it tell you which? It didn't say which one it used. Okay. Which apparently is a couple different ways, but I think this is the one that's in the book. And through kind of using some magic calculations, but basically you have to, it has a lot to do with breaking down the extended Euclidean algorithm, which I still don't fully understand. Involves basically figuring out the quotient and the remainder. And I think there's actually a trick you could do too, I think, because you know that both these numbers are relatively prime. So you divide this by this, you get 40. I have to remember how this works. So you basically go down this left column here, keep dividing to get the remainder. To once you get a remainder of 0, and then this remainder, you're just rounding. You don't care about any decimals that you that you're left over with. And then once you have those, you basically work your way back up. So you go from, so you can rewrite this form. I guess this is a better one. This 19 equals 6 times 3 plus 1. So you can basically rewrite this formula as this. Right, because it's got a remainder of 1. So basically 6 times 3 is 18 plus 1 is 19. And that's kind of a way of doing the module algorithm. And I think this algorithm is really designed to be optimized for computers. I think you can do some fancy bit shifting and stuff too. And similar with this one, this is 3 times 19 plus 3, because the remainder is 3, will equal 60. So you can kind of just stack those back up. And then what you can do is you can rewrite it again where you have 1 equals this formula. In this case, we're getting the remainder. So we want 1, and then we got 3, and then 19. And when we rewrite that, we can substitute. So this 19 times 6, and then this 3, we know that 3 here equals this formula here. So we substitute that in. And once we've substituted that in, we end up with this formula up here, which you can kind of rewrite to get back to that original one where you got the multiplication plus the multiplication. That's the formula we want. So if you remember, we wanted this formula up here. We want to figure out what x and y are. In our case, we just want x. So, and then you just you keep repeating this process as you climb. So you climb down, and then you climb back up here. So you keep repeating this process. So you should end up with the 6 times 60 and 19 times 9. So you take this 19 and you substitute in this formula here. So you can see we did that here. And readjusted everything so that we ended up again with the plus and minus there. So now we have 13 times 60. And then if you substitute the 60 in there, with this formula, you're going to end up with, oh, it's word wrapped here. Let's, all right, so then you end up with this formula here. And this is the number that you want. This, so basically this x, the 79 is just on the different side of the formula because I did them just when I was writing the formulas out, I did it backwards. But this is the number that you want. This 1019. This becomes your private key. And again, there's some Python. If you just Google how to calculate this, there's some Python scripts that'll do it for you, which we might end up using when we do the actual algorithm here. So using the extended including algorithm, we get a D value of 1019. All right, so now that we have that, just put this down here. Okay, so there, now that we have that, so say if we wanted to encrypt the message, let's encrypt, this part I haven't really rehearsed, RSA. So, and then let's say RSA, I have to convert that to binary, which I don't remember how to do in Python. Is it two char? I don't remember now. All right, let's do this. Convert string to binary in Python. Let's see if Google or there we go. Okay. All right, so it's we're at string to not binary. String to ASCII, let's see, in Python. There we go. ORD. Okay, that's the one I'm looking for. Oh, no, come back. Okay. So if we did RSA dot join ORD C for C in, oh no, whoops, this needs to be blank, in RSA. Oh, what I need a bracket, there we go. Oh, did you tell me the wrong? Oh, shame on you, Copilot. Is that not, do I need single quotes? Ooh, let's see. I'm not really a Python. Okay. I'll have to look this up. Okay. Python convert string to ASCII. Oh, clear, of course not. Oh, join string ORD. Oh, I forgot the string. It was right. I just forgot this part here. All right, so there we go. So now this is really 82, 83, and 65. So those are numbers. So you have to convert the string into numbers for the conversion to work. And there's also some, I can't remember the exact rule is, but you can't encrypt a number that's bigger. I can't remember. I think it's bigger than E or let me see now. Anyway, there's a limit to how big you can encrypt. So I think when you're using much bigger encryption numbers, you wouldn't encrypt like one character at a time. You'd encrypt a giant block of characters, you know, say like a meg or whatever, just a huge amount of them. And you would do those in blocks. So, but in our case, we want to encrypt, so we're going to need 3 letters for our message. So see if source our message C1 is going to equal, we need to run the encryption on it, which is 82. Oh, I think it'll fill it all in there for us. Yep, mod 79, or to the power of 79 mod. Let's check if that's correct. 82. How do you do the power in Python? Python power math. How to do math in Python? POW. Oh, okay, it's just POW. Okay. So if we do the POW of, I'm assuming 8279 mod 3337. So remember, this is our n value, 3337. That's n. So this is our this is us encrypting. So someone shared us with their public key. They shared this with us, and they want us to send a message back. So we're taking their public key and encrypting that back. So, what's the percent symbol? Sorry. There we go. So, oh, that gave a different answer. Did I do that right? POW. Let's see, POW. Ah, there we are. Power and authority. Return x raised to the power of y. Yeah, okay. So 82 raised to the power of 79. And remember, we picked 79 because that's our e value. Yeah, I guess it's 2. Well, I'm going to say it's 274, but maybe that was right. Okay, so C2 is going to be 83. So let's see if that one. POW of 83 to 79 to the power of mod 3337. All right, so that one equals 2251. It's funny how you can be off by just a little bit and it changes the number so much. And then C3 is going to equal that one. So what do we have? 65. 541. Okay. 541. Okay. Okay, so now we have these three things. I think we'd probably pad our message with just some extra stuff to get everything the same, so it would look something like that. And this is the message that we would send, so M would look like this. And now when someone needs to decrypt it, assuming I did my math right, let's find out here. You just have to repeat it, but going backwards. So in this case, we know we're going to get 4 blocks of 4. So we'll just unencrypt those in blocks of 4. Assuming I did this right. Let's see. I don't know. Let's find out. Okay, so then we'd end up with like M1 is going to, so if the decryption one is basically this one. So this is where we use D. So we're going to take C, the decrypted part, and we're going to take it to the power of D. So 0274 to the power of 1019, and then yeah, mod 3337. Okay, and we'll see what that should give us 82. Let's see if we did our math right. So we got pow of 274, so 1019, and then we'll mod that by 3337. Oh, yeah, 82. Oh, okay, cool. So I did do the math right. Hooray! So then we just repeat that with the other numbers, which is 2251. That gets us 83. And then M3 equals, what's that, 541? All right, 65. All right, and then we're just back to our original message there. So that's basically how the algorithm works. So now let's use that knowledge for decrypting this one, just not without using a little bit of math and not just randomly plugging it in there. So let's put this to Pico. All right. So the first thing, let's just put our values, let's just cut and paste them out of this file into here. Okay, so that's what we have. So the first thing we need to do is we need to figure out P and Q. And the reason we can figure out P and Q is because this is actually not a very big number, this N. And if you actually got this idea from here, if you look up here, they list this FactorDB database. So there's some math you could do to try and figure out what N is. Like, you could run through it, but it took a while. I tried creating an algorithm, but it took so long, even with this unencrypted one. But this website here, as far as I can tell, is basically a database of factors for like prime numbers factors. So you can enter any old prime number and it'll show you what the factors are. Just here's your P and Q, just like that. And I'm assuming it doesn't do anything, it just looks it up. So and then we got this is our P and Q. P equals, so it doesn't really matter which one is P and which one is Q. Right, so you got one I think that's right. Did I copy that right? 09. Yeah, 40 and 42. So let's see. I'm curious. Let's see. Like, if we just entered, what's another prime? Like 7. Was it just going to find it? Yeah. Or I guess this is, how does this work? Factor tables. Yeah, like I'm assuming this is just a giant database of, yeah, like all the primes. Yeah, composite numbers with their own factors. Like, this is, every time they find one, they just add it here. So if you pick a small one, there's probably a database with your numbers in there, which is it's always kind of scary. That's why we have to keep getting bigger and bigger encryption values. Reminds me when I was many years ago at the U of A, the University of Alberta, checkers was a big kind of one of the claim to fame at the time. Was there was a fellow, I think his name was Jonathan Schaefer, who was working on checkers and AI for playing checkers. And so they had a pretty good AI that would compete against the world champion checkers player. But eventually, if I remember correctly, they just ended up creating, this is much later, I think after I left university, they just basically created a database of all the possible checkers moves. So before, from my understanding of the way chess and checkers, a lot of those algorithms work, once there's reduced number of pieces, then it's just a database lookup of what to do. But before that, it has to use some algorithms and play the game a little bit. But checkers, to my knowledge, is a solved problem. All the possible checker moves are available. So it's the same thing with these prime numbers. People just keep factoring them in. So yeah. Oh yeah, look at all those stats here. Oh, it's interesting. Okay, so that we figured that out. So now that we know P and Q, the next thing we want to do is we want to figure out D. So if you remember how to figure out D, you had to use this extended Euclidean algorithm, right? So D was basically this formula here. So so in this case, D yeah, well, if we refactor it, so it's D times E. So D times E equals 1 mod. This is this P minus 1, Q minus 1. So we know what E is, right? So we can substitute E in as this number, right? And then we also know P and Q now. So it's really, oh, what did it do there? It threw that big number. But we really have this. So it's like this minus 1. Let's put some brackets around that. And then this number minus 1. So that's the formula we're trying to solve for. But obviously this is going to take a while. So we're not going to manually solve this one. Let's go look it up here. There we go. Oh, I already it's already got it in here. So is this the right one that I want? Modular. Oh no, I can't remember. I did all this a while ago and I didn't. I should have taken better notes now. Here's me playing around with more of the numbers. Calculate N, calculate D. Oh, I just put N in there. So what is that? Oh, let's try. How does this work? One. So let's see if I can put these two numbers in. I'm just curious. This is me just mucking around. Minus 1, so that's 2. And then this big number here. Minus 1, so it's 8. And then our number is this. All right. I don't know if that... Yeah, it's probably not what we wanted. Oh, here. Extended. Let's go to here. This is what we want. This extended GDC calculator. So we want this number here. All right. Why aren't you listening to me, Visual Studio? There we go. All right, there we go. Let's try this. Minus 2. And there's actually Python applications you can. Sure, let's show the algorithm steps. So again, this is where it's gonna go up and then down. So it goes. Oh yeah, look! Wow, look at all that. If we did that manually. Okay, let's not show those and just give me the answer. Okay, so we want We got U and V. Is that what I want? Oh, this one still confuses me. Like, here's the algorithm right here. So it's we don't want this. I think we want this positive one here. Okay, so I think this is the number that we want. So this, I believe, is what D is. Let's try it out. Let's see if we can decode our message here. Is that what we want? Huh, I don't know. Let's see. So let's take all right, so to decode it, what's my algorithm again for decoding? This one. Okay, so I need my C message. I don't know if the whole message will fit. Let's see. So just paste that. So it's, whoops, I need to do pow of this to the D, which I believe is this. Mod, and then N. What the heck is N again in our case? This one. All right, let's see what that gives us. I don't. Maybe this will. Those are some big numbers. Oh yeah, no, I think that's wrong. Okay, that's never going to complete. All right, so I think this is the number I want. This 5. Okay, so I don't actually. What I really need. So to calculate this reverse mod here, I actually need to figure out what. Sorry, I need to figure out what this is here. So let's copy this. I think that's a number I have up here, but I'm not sure. We need like a multiplication symbol here. All right, there's the big old number. All right, so 5, 2, okay. Oops, no, why didn't you copy that? Oh, go away. Can I copy just 5, 6, 5, 2, 5. 5, 6, 5, 2, 5. Is that really what D is? I don't think it's this one. Let's get rid of that. Okay, so let's see if we can calculate the message from this. So C, again, I don't know if you should take this whole message or not. Wow. My guess is you're not supposed to take the whole message, probably just chunks of it. I'm not sure how big of a chunk though. Mod. I don't know if that'll complete anytime soon either. All right, let's go back here. Take a look to compute all the numbers. What did it figure out D was here? D. Oh yeah, no, D needs to be a really big number. 8. Oh, I'm doing something wrong. Okay, so we got P. Yeah, we got P and Q, no problem. This is P and Q, P minus 1, Q minus 1. That's this thing here. N is, N we obviously already know. So we got the wrong D. How did we get the wrong? So this is what our D should be. Oh, it's actually completed. Wow, crazy. So this is what the D should be. Now, what did I do wrong here? Oh, my N is the wrong. I put the... No. So we could rewrite D as... Right, which is the same as D equals E, yeah, to the -1. Oh, right, I have this. Okay. So we have E. Oh, I had those numbers backwards, I think. So we have E, which is this. Boom. We have did I say that N minus P? Oh, I need that number again. This one here. Oops. Copy. There we go. Okay, I had the numbers backwards. Sorry about that. Now I need to somehow copy this without that stupid thing pop. Oh, there it is. Okay. Yeah, that's the same. Okay. There. It's mostly live, right? So, all right. There. That is our D. So now we should be able to, I don't know if this will work. Let's see. So we take C. So we need to do the POW of C, which is this, whoops, Control-Shift-V, this ridiculously big number, to the power of this D, and then we mod it by N, the public key. Oh. All right. Oh, that's not right. Sorry about that. Let's try this again. POW of. All right, let's just go slow. I'm trying to do shortcut keys and they're not working. So the POW of that times no, to the power of D mod. Okay, so I have the C, the message here, yes. I have D, which is here. And then, wait, is that the same 409? Oh no, they have this. That's interesting. They both start with the 862, and then in 409, but everything in between is different. Okay, and then I need to mod it by this ridiculously big N number. Yeah, they really look the same, don't they? Okay, let's see what that gives us. And that'll probably give us something, I'm assuming, in ASCII. So let's see. That's probably not the most efficient way to do that. I'm sure there's a way more efficient way, because this, I don't know, this is bringing my computer to its knees. Oh, that's crazy. Because the other thing we could do is we could just have a, let's see what other calculators they have here. Oh, there we go. Yeah, so maybe we'll just try it in here. So we have the base number, which is this. We have the exponent, which is this. And then we have the mod. All right, so we got this back. Okay, so that's taking forever. So our M equals this. Now let's convert this to ASCII. I don't know a way to do that in Python, but this thing has a yeah, we want the hex. It's not hex. Oh, what would this be in? What did it dump that out in? Well, we can also try this too. CyberChef. I wonder if that's right. 75 input. What does the wizard say? From base 85. That's not what we want. So this is really ASCII, I think. Is there anything about ASCII in here? ASCII. This would be like, which one of these do I want? Anything Unicode? Oh, maybe this one. Yeah. Okay. Now, well, let's take it. Let's ASCII chart. ASCII table. All right. So if we look up 79, or no, 75, it's a K. Oh. Is there something else going on with this cipher? So I put that as the base. This is the exponent. Wait, are these the same? Oh, these are the same numbers. I screwed that up. Oh, my apologies. Sorry about that. So, what did I do wrong there? So I want e to the -1. Oh, so I need to do this. There, maybe that's a better one. Is that a better D? What D did we get here? Should have written that down. Oh, it was an 8. Why is D the same as N? Oh, did I? Oh, somehow I replaced this N. Oh, okay. I'm not sure when that happened. When I'm watching this back, I'm sure I'll see it. Oh my god. Okay. Okay, so let's go back to here. All right, so we want C. So we want this C. Yep. We want this D. And then N is this. All right, let's double check that I have the right numbers in there. So 4 C to the power of D, which is this. And okay. So this is what my message is. Now, does that help us at all? Because the first one should be a small case p, which should be 100 and it's not in hex, is it? Is that base 64? Maybe? Because 13 is a carriage return. That's no good. Oops. So what should the actual message be? Plain text as an integer number, sure. Oh, okay. That's the same. That's good. Yeah, okay. So this is the correct number. Now I need to convert this somehow to is this base 64? Is that what it is? No, it doesn't. I doubt it. Yeah. Convert to integer number. Yeah, we're at base 10. So if we try this, all right, is this going to tell me? Now I want base. From base 10. Oops, 10. Oh, that doesn't help. From base 64 will produce something that's not very useful. Now, how do I get this to? How do I get this to an actual? Because I'm pretty sure the answer, like if I just look at the plain text, it's just going to start with PicoCTF, right? Yeah. So that's the answer we want. Now, how do we convert this to that? Because a P, well, what's the closing curly brace? That's 125. Let's see. RSA integer to ASCII. Oh, what's the byte size of? Oh, okay. Maybe there's some padding in there. Convert to binary encoding of the number. Oh, PicoCTF1. Is that what I need? Let's see, PicoCTF. Or integer from decimal. Oh, maybe this is it. Data is not a valid byte array. Yeah, that's fine. Okay, I'd have to convert this to bytes first. Byte. Oh, I don't know how to do that in CyberChef. So you need to have the... No, big integer returns that when we size signed big Indian octet strings. Oh, is it actually base 64? Oh, it's looking pretty... Oh, I probably have to reverse it. Yeah. Oops. It's raw. Oh, let's do it after. Do I? Because that's pretty close to what we want there. Like there's the closing brace and everything. Oh, we're pretty close here. Now, big integer byte returns any size. Okay. Well, it's almost been an hour. I should figure this out real quick. Maybe. Pressure's on. So that's pretty close to what we want. There's probably some other garbage in there. Okay, so what do they recommend doing here? Convert to integer. Well, it's base 16 to base 64. Is that what they're suggesting? Convert to integer number. So I gave us integer. Can you do all right. Bytes to integer and integer to bytes. Where it's an array. Let's see. What if we change this to is there 2 bytes? What was that? Put it into bytes. That one's got a couple negative answers. Octet string bytes. Simply interprets the bytes as an unsized big Indian number. However, converting the text to bytes. Right, from base 64, that's not what we want. It's pretty close though. Right. How do I make a byte array? CyberChef byte array. CyberChef create byte array. Okay, let's see. Big number. Yeah. Strings. Oh, okay. Nope, not what I want. Ah, no, that's helpful. Oh, it's so close. Right, we did from decimal. That was the one that gave us. Oh no. Okay, let's just do this. Python integer to byte array to string. Oh, okay, so there's a 2 bytes. So if we take this, and we go this, dot 2 bytes. Oh, do I need to give some more options? Integer's too big to convert. Awesome. Python. Okay, let's try this. RSA integer to a string. That integer's too big. So string to integer, you take m. So the I dot bit length. Oh, so it's math dot ceiling of dot bit length divided by 8. What's going on? Okay. Invalid decimal literal. Oh, do I need the brackets around it? Oh, okay. So, and then divide that by 8. I'm going to take the ceiling, so 33. So, so we need to take this ridiculously big thing, dot 2 bytes, length is 33. I don't know what the byte order is, but we'll see. Hey, there we go. Okay, cool. We did it. All right. Okay, well, let's wrap that up here. So thank you very much again for coding with me. I hope people find these interesting. I don't know. I like doing it. It forces me to... There we go. Forces me to learn some new stuff and play around with stuff. So if you have a question you want me to answer in a future video, send me an email to ask at SaturdayMP.com. If you stuck around for this entire thing, or leave comments down below, that would be great. If you stuck around for this entire thing and found this useful, please hit the like, subscribe, all those other things, so other people could find this, or just share them with them if you if you're like, hey, you want to see some idiots struggle through RSA? There you go. If you have some better ways to teach RSA, let me know too. Maybe we could pair on it in a future video, or I'd love some advice or feedback. So thank you everyone for watching. I hope you have a great day, and I will catch you in a week. Well, I've been trying to do these weekly, but it's been every 2 weeks because life's gotten busy. So maybe in a week or two. Take care. Bye.